Good morning, chemistry. We're going to shift our focus a little bit this morning. We were going to talk about acid dissociation, which we'll talk about tomorrow. I mean, there's not much to it. It's very similar to what we've been doing, but I wanted to go over the exam with you, and then if I'm a smart feller, I'll unlock so you can see your answers and get and see where you made errors and stuff. And a lot of it was just same as it was before, just wording and maybe kind of missing the factor that was going on. Anyhow, I have it pulled up here. It's a little different format than the online format, but the questions are all the same, essentially. I may have made some typing adjustments, like I can see here. I said left, right, or no change, whatever on it, which is what this should say. So anyhow, you had some equilibrium reactions to start with, and I think most of you figured it out by the directions. These were not multiple choice questions. They were just regular questions you had to answer each part. So the idea was here, like here you have this equilibrium expression. It's an endothermic reaction of nitrogen and oxygen mixing to make nitrogen monoxide. And then for each of these, you were supposed to say whether the reaction would shift towards the left, towards the right, or maybe no change. Okay. Now, adding in oxygen. Here's our oxygen in the reactant side. If I add in more oxygen, that is going to overload the left side. It's going to shift equilibrium to the right. So the answer for A was right. Decrease in pressure. This is the one that people have troubles with once in a while. And this one was a little trickier than most. This separated the A's from the A minus, or the A's from the B's, or whatever. But if there's if pressure goes down, volume goes up, and you want to go to the side with the most moles of gas. And you look at the little things under here, and you've got 1 mole of gas, 1 mole of gas, that's 2 on the left side. You've got 2 moles of gas on the right side. They say, well, they're equal. Then you got to remember that tiny little quiet second part of the pressure volume thing. And that is, if you can be more gases, that's more disordered. That's what you want to be. So it's more moles or more, more different gases. And so the shift for B was left because while they have the same amount of moles, you have 2 separate gases here as opposed to 1. Anyhow, that was one of those, again, that's one of those little things that separates the A's from the B's. An increase in temperature, it's an endothermic reaction. So heat's loaded up here on the left side. It's going to shift it to the right to get rid of the excess heat. Remember, with heat, you can kind of look at heat like you look at concentration. That if you're adding to the side the heat's on, it's going to shove, it goes away. If you remove stuff, then it replaces it. And here, removing the nitrogen, if I'm taking the nitrogen away from here, then it's missing, then it's going to shoot left. It's going to shift left to replace the missing nitrogen. So we went right for A, left for B, right for C, and left for D. Really was the same thing here with the uranium oxide mess extravaganza. Again, is the direction going to shift to the left, shift to the right, or have no change? So here, if we add some more uranium oxide, well, uranium oxide's on the left, it's going to shove it towards the right. So A was right. B, I think many people did okay on this one. It's good for you. The reaction is performed in a glass reaction vessel. The hydrofluoric acid attacks and reacts with the glass. Well, if this hydrofluoric acid here is reacting with glass, then it's not part of this reaction, so it's getting removed. Okay, that's the idea. If one of those, and that was kind of like our lab, especially with the ammonia acid precipitate part. If you put in something, if you have something here like the hydrofluoric acid that's going to react with something that's not in the equation, then it's going to remove it. So by removal of the hydrofluoric acid, then you have to shift left to replace what's missing. So B went left. C, the catalyst, most of you got this, good for you. Catalyst introduced. catalyst has really nothing to do with equilibrium because both directions are going to be affected equally. So while it'll get to equilibrium faster, it won't change anything. So that's a no effect. And then D, pressure is increased. If pressure goes up, volume goes down. If volume goes down, you're on the side with the least moles of gas. This has 4 plus 1 is 5 moles of gas. And this side only has 1 mole, 1, 2, 3 moles of gas. So it's going to shift right. So for 2, A was right, B was left, C was no reaction, and D was to the right. Now here on the smelling salt equilibrium, and you're supposed to explain what's going on, we had some explanations that I think you would have got full credit if you'd said the right stuff. Some of you said the right stuff with the wrong answer, and vice versa. You had the wrong answer with the right explanation. So it was rather interesting. Old-fashioned smelling salts consist of ammonium carbonate. You should know that by reading now. And it decomposes, and it's endothermic, which means the heat's going to be on the reactant side with the ammonium carbonate. That's the whole point. That was the key part of the question to see if you remember what endothermic and exothermic was. The heat's on this side. So then it asks, would the smell of ammonia increase or decrease if the temperature is increased? So an NH3 is ammonia. So are you going to, if you're shifting the equilibrium to the right, then you're going to get more of an ammonia smell. If you're shifting it left towards the ammonium carbonate, then you're going to get less. Well, if the heat is on the left, because it's endothermic and you need the heat to break down the ammonium carbonate, then the equilibrium is going to shift to the right and you're going to get more of a smell. Now, you couldn't just say more of a smell. You had to have the wording and the explanation that because heat's in the reactant side on the left, by increasing the heat on the left side, you're shifting the equilibrium to the right side. And so to get full credit, you not only had to say that the smell was increasing, but you had to explain that it was endothermic shifting to the right. Okay. The next one, the why you shouldn't ever be eating candy and drinking soda and all that junk, another equilibrium one. And what you have here is you have the equation for tooth enamel, and tooth enamel is in an equilibrium of breaking down into calcium phosphate and hydroxide ions. Okay. This is very much like that question of the hydrofluoric acid in the glass above. Okay. What it says is when sugar ferments on the teeth, it kicks out hydrogen ions. It's acidic. Okay. I'm just going to kick this down so you can see the equation better. All right. And then the question it asks is, when the sugar kicks out the hydrogen ions, what effect does the increase in hydrogen ions have on the tooth enamel? Does the concentration increase or decrease? Now, this one, again, full credit was all about the explanation because you could take a 50-50 guess at increase or decrease, but that doesn't mean you know what the heck you're talking about. And here was the difficulty. There's no hydrogen ion here. It's not directly in the equation. So it's not adding to anything. It's not adding to hydrogen. There are no hydrogen ions. So any of you who said it's increasing the hydrogen ion concentration, therefore shifting the equilibrium, you're wrong because there was no hydrogen ion concentration. Okay. Now, a few people got this right, but this is again, one of those concepts of if the hydrogen ion gets thrown out here, so you got this reaction equilibrium. Then you eat a bunch of candies and, whatever, a Snickers bar, Mike and Ike's, or anything else that's going to rot your teeth and make you, gum your food the rest of your life. The hydrogen ion, look at what's here. Hydroxide ion. So if I have this equilibrium on my teeth that is kind of rolling back and forth and keeping the enamel in place, and then I eat candy and I let it sit there. I don't brush my teeth and neutralize the acids and stuff. then what it's going to do is it's going to bind with the hydroxide and make water. Because hydrogen ions and hydroxide ions love each other far more than anything else going on here. So when I eat the candy, I produce the hydrogen ions. They're going to bind with the hydroxide ion. So what's happening here is it's removing the hydroxide from the equation. That's why I say it's just like that question above with the glass. It is removing the hydroxide ion from the equation. If this is getting removed because it's binding to the hydrogen from the sugar, then you're losing it. So the equilibrium is going to shift right to replace the missing hydroxide that the candy was drawing on, which means your tooth enamel is going to decrease in concentration because the hydroxide is being removed. Okay? 5, this was the same type of question as the other ones above, but it was an increase, decrease, or no change. So it was, for example, here in A, what's going to happen to the concentration of the nitrogen monoxide right here when more chlorine is added to the reaction? So we did some of these in our homework. So this was saying increase, decrease, as opposed to left or right. Okay. Now, here's my nitrogen monoxide on the left. If I start piling on some chlorine, then I'm overloading the left side, so the equilibrium is going to shift to the right side. If the equilibrium shifts to the product side, then everything on this side is going to go down in concentration. So A is a decrease because you're going to lose nitrogen monoxide as the equilibrium shifts to the right. How about this mess, this nitrogen monoxide? It's got a common name that I can't think of right now. It was just on the tip of my tongue, but the NOCl, this covalent compound, if you heat the reaction. Now again, if you're heating the reaction, you're overloading this side, you're going to shove the equilibrium towards the left. If you shove the equilibrium towards the left, then it means everything here on the right is going to decrease. Okay? So B is also a decrease. All right? How about chlorine here when the volume is increased? Okay. Volume goes up, pressure goes down. All right. And you want to shift to the side with the most moles of gas. So look at their little subscripts. I got 2 plus 1 is 3 and 2 over here. So it's going to shift to the left because there's more gas there, which means that everything on the left is going to increase. So C was an increase. And D, the nitrogen monoxide, when I cool it off, if I put this in an ice bath and cool it off, that means the heat's being removed. It's going away, so the equilibrium is going to shift to the right, which means that the nitrogen monoxide is going to decrease. So A was decreased, B was decreased, C was increased, and D was decreased. Okay? And then the last couple reaction rate ones. 6, we miss this far too often. For those of you who kept, I'm going to say it this way because it sure looked this way by the way you typed in your answers. And for the folks who I knew in class were always talking to each other. Whoever went out and said catalyst and spread that word around on catalyst, you made everybody completely wrong. Okay? This is why it's best to do your own work, think by yourself. Now, that doesn't mean the people that were thinking by themselves didn't see catalyst, but boy, the almost exact wording of these, again, am I going to chase you? I could easily print out these exams and go to somebody and have a lot of suspicion. Am I going to chase you down because you're cheating? There's too much going on to worry about with distance learning than some of you who are trying to cheat, get it wrong anyhow most of the time. And all the ramifications that are going to come later, even if I don't turn you in. Because I'm telling you, it's going to come back to haunt you. And where it haunted you here is you got everybody lost at least 3 points because I was generous to just almost give you 1 point just for answering. All right, zinc reacts with dilute hydrochloric acid to produce zinc chloride and hydrogen gas. Okay, that's nice. It doesn't really mean diddly squat. The key is the next sentence. When zinc powder, P-O-W-D-E-R, little grains is used instead of big chunks of zinc, the reaction is faster. Why? Just read the question. Powder versus big chunks is a surface area question. There's much more surface area in the powder. You're throwing that powder into a liquid acid solution. It's going to spread out as it hits the water, so much surface area in there that your opportunity to collide, and again, both these last two questions had to relate exactly to collision theory, talking about your improving the opportunities and the odds of colliding at the appropriate energy level and orientation. So on this one, it went faster with the zinc powder because it had much more surface area and had increased, greatly increased the opportunity for the particles to collide at the appropriate energy and orientation. So much more powder surface area when it goes in there and dissolves in the liquid, as opposed to dropping big chunks down to the bottom where it has to start decomposing the stuff on the top before it can get to the middle. So 6 was a surface area question. Too bad for those of you who spread the word on catalyst, because you were way off the mark. Okay. And then 7 was pretty straightforward. Again, really a lot of the reason people just got this wrong is they said, well, the temperature was higher in experiment 2, so it went faster. Yes. Yes, but that's not what we're asking. I mean, that is what we're asking you, but that's not the explanation that's required. Evaluate the results. So you had the 2 experiments. They had the same concentration. They had differing temperatures. They had same mass of zinc, same size of zinc. Okay, everything going on. Very similar to the reaction above. So the only key factor here was the temperature. In experiment 2, the temperature went up. If the temperature increases, the kinetic energy of the molecules increases, and therefore they have a greater chance of colliding at the appropriate energy level and orientation because they have more energy. Anyhow, most of you got that right except for maybe a cruddy explanation. But the biggest errors came in here. For some reason, whoever came up with catalyst over surface area didn't work. And here, very few people noticing that the hydrogen, this is a removal question. The hydrogen is going to remove the hydroxide and therefore drive things that way. There you go. So that's that for today. If you haven't done so, then you have today to finish your pH homework, that chart that we went over yesterday, kind of how to do the math. Just get that uploaded today, and tomorrow we'll start in with acid dissociation and really how to tell what a strong or weak acid is, because pH doesn't quite do it. All right, there we go. That's it. Have a great day. We will talk to you soon.